Dealing with a process that has a long dead time may affect the controllability of your process. And I'm going to show you an example of such a process where we are going to have a long dead time. And I'd just like to show you a quick way to calculate the PID values, which may get you out of trouble and allow you to go and control the process. Let's put this into perspective. I've got a process in front of us and it's just got PI values that I have gone and put in. The process is in automatic and it's got virtually no dead time. So if we were to change the set point of the process, you can see that the process variable responds immediately. The process variable is the red pen. The output from the controller is the blue pen. So as the output changed, so the process variable went and responded immediately. Now, my time scale is in minutes. Again, from left to right, every green block is going to be 5 minutes. I'm therefore going to go and put in a time delay of 3 minutes. As I change the set point, you're going to see that the process variable will take 3 minutes before it responds. And that is going to have an influence on my process. Immediately, you can see that the process has got slight oscillations because of the time delay. So it is not as crisp as it would have been. Let's go and put in a dead time of 5 seconds. 5 minutes. I have gone and put in a dead time of 5 minutes. Now when we change the process, you can see that it takes 5 minutes to respond. And when the process does respond, it becomes quite oscillatory. It's up and down all over the place. Great. And of course, if we were to make that dead time any greater, the process would get even worse than that. I'm going to go and give it a dead time of, let's go and say 8 minutes. I don't even have to change the set point. And in this case, you can see that my process is going to run away. It's just going to get worse and worse all the time. So this is really going to be very bad for control. Now that is with a dead time that we can go and have of, we've had at a value of 8 minutes. Imagine if I was to go make that dead time even longer than that. In fact, I'm going to go and put in a dead time on the simulator, which will have a value of 20 minutes. Now you saw that the process became uncontrollable with a dead time of 8 minutes. Imagine if we were to go and put in a dead time of 20 minutes. All is not lost. I have found a set of equations that will work for us, and I'm going to put those up on the screen next. This is the set of equations. You need to go and calculate the process gain, which is always going to be the change in process variable divided by the output percentage that caused it to go and change. You're then going to take 0.3 and divide it by the gain of the process that you've just calculated in order to get the gain value of your controller. My integral time is going to be 0.42 multiplied by the dead time, or 42% of the dead time, and we're not going to use derivative action at all. In order to get these values, you need to have a self-regulating process which you will put in manual and then go through the following steps. We start off by taking a process, putting it in manual, and maybe take it to a low value. I'm going to take my output down to 20%. Now, as you can see, there's going to be a 20-minute delay before the process variable starts to respond. And I will take it down to that value and then just go and jot down what the values are going to be. Now, I'm just putting on the data monitor, and you can see that with an output of 20%, my process variable is going to sit at 30%. Then what I do is I give the process a step change. In my case, I'm going to take the output from 20 to 50%, and we'll have a look at the response of the process and see where the process variable is going to move to. After the 20 minutes, my process variable starts to respond, and it looks like it's going to go up to a value of about 75%. I can go and pause the process and write down all of the values and go and do the calculation. As we've just seen, for an output of 20% in manual, the process variable went to 30%. And for an output of 50%, the process variable went to 75%. So what we need to go and do is calculate the changes in value. The change in the output would be 50 minus 20, which is equal to 30%. The change in the process variable would be 75 minus 30, which is going to have a value of 45%. Go and calculate the gain of the process, which is the change in the process variable divided by the change in the output, which would have caused it. And that would have been a value of 45 divided by 30, which is going to give you a value of 1.5. Then you can go and calculate the gain of the process, and we have got the formulas over there. The gain of the process is going to be 0.3 divided by the process gain. In other words, 0.3 divided by a value of 1.5, and whatever that gives you is going to be your new gain. 0.3 divided by 1.5 seems to give me a value of 0.2. Then we're going to go and have a look at 42% of the dead time. Now, I did say to you that my dead time was going to be equal to 20 minutes, and therefore 20 times 0.42 is going to give me a value of 8.4 minutes per repeat. And those are the values that I would go and put into my controller. We're not going to use any derivative, and therefore the derivative is going to have a value of 0. So we're going to go and put in 0.2 and 8.4. Let's get to my simulator right over there and put in a value of 0.2, 8.4, and we can now go and run the process in automatic. Remember, it's not going to take away the dead time, but it is going to allow you and I to at least control this process of ours. And as you can see, the process variable is making its way towards the set point. Let's go and change the set point and see what type of response we're going to get. Again, it does not take the dead time away, but it does make the process quite controllable. And as you can see, the process variable is now making its way towards the set point. Yes, there will be a little bit of an overshoot, but it will do its best to control the process and get it to exactly where we need to be, which in this case is going to be at set point. And that is it. That would be a nice, quick and easy method that you can use for processes that do have longer dead times. And I would typically say where a controllability factor of mu is going to be anywhere between 1 and 5. This method does work very, very well. As always, you do have the link below, which will take you straight to many of the different courses that we can go and present. Thank you very much for your time.